thank you for joining me today. Today's video we will discuss about Buchwald precatalyst, which is used in a variety of transformation to create CN, CC, CO, and CF bonds. Did you know there are 6 generations of Buchwald precatalyst? It can be pretty confusing, right? In this series of videos, I'll walk you through all of them. We'll start by looking at their structure and how they get activated. Then we'll take a closer look at each generation, learn about their history and applications, and understand their limitations. So stick around to get a clearer understanding of Buchwald precatalysts. First off, these precatalysts are named after the American chemist Stephen F. Buchwald, who made a major contribution to developing these catalysts. But when catalysts are widely used in palladium-catalyzed cross-coupling reactions, they are great for efficiently and selectively forming bonds between different organic molecules, making them essential for synthesizing complex compounds. Alright, let's start with the first generation of Buchwald precatalysts, which were first published in JACC back in 2008. This complex made of phenethylamine, a chlorine, and a phosphine ligand. The authors explain that it can be deprotonated in the presence of a base, followed by a CN reductive elimination to produce an indolent and the active palladium zero catalyst. In 2010, Buchwald's group introduced a new class of second-generation X-phos precatalysts, where the phenethylamine, an aliphatic amine, is replaced by a 2-aminobiphenyl. The 2-aminobiphenyl, an aromatic amine bound the palladium center, shows a higher acidity when comparing to the aliphatic amine, or in another term, we can say it has a lower pKa. This high acidity allows the deprotonation in the presence of a weaker base at room temperature. This activation followed by a CN reductive elimination to give 9H-carbazole and the palladium zero active species. As you can see here, the replacement of chloride in the second generation of Buchwald precatalyst by a more electron deficient and less sterical hinder gives the third generation G3 precatalysts, which are the most versatile and can accommodate very bulky ligands, such as those in the Bradford family. It is likely that palladium G3 can handle these larger ligands because the mesylate anion can dissociate from the palladium center, unlike in the chloride in palladium G2. When activating the G3 precatalyst, it undergoes deprotonation to form a palladium amido complex, which then reductively eliminates to produce the active palladium zero, a metasulfonate salt, and the carbazole. In some rare cases, the carbazole can inhibit the catalysis by consuming valuable reaction feedstock and also complicating the workup purification. To circumvent this issue, the Buchwald group prepares the fourth generation and the fifth generation by methylating and arylating the amino group on the aminobiphenyl scaffold. During the activation, deprotonation of G4 precatalyst gives palladium amido complex, which then reductively eliminates to yield active palladium zero, a metasulfonate salt, and 9-methyl-9,8-carbazole. For the fifth generation, the deprotonation of G5 precatalyst gives a palladium amido complex, which then reductively eliminates to yield the palladium zero, a metasulfonate salt, and 9-phenyl-9H-carbazole. The Buchwald resist precatalysts are oxidative addition complexes that release the active palladium zero species by reductive elimination without requiring a base. They are air and moisture stable, easy to handle, and highly effective even with bulky pyriphosphine ligand. So, here's a quick overview. For the first to the fifth generation, activation occurs in the presence of a base, followed by reductive elimination to produce the active palladium zero species. For the sixth generation, no base is needed. The active palladium zero species formed after reductive elimination. Thank you for watching and see you in the next video when we dive into these activation modes in details. Have a nice day. Bye.